In algebra, factoring an expression means breaking it apart into two or more expressions which are multiplied together, and that product is equivalent to the original expression. There's a wide variety of methods to factor an expression in algebra, ranging from the simple to the quite intricate. And even worse, factoring an expression is not even always possible the way that we want it to be. But let's start out with the simplest method of factoring an expression possible, which is to, among an expression with multiple terms, factor out a monomial, a single-term expression. To factor a monomial expression out of a polynomial, such as the one we've written here, let's first remind ourselves that to factor means to break the expression apart into one or more pieces which are multiplied together. So I'm going to write a blank shell of one expression multiplied by another expression in parentheses that we're going to try to fill in a way which, if we were to re-multiply that expression back out, we would arrive back at the original expression we started with. So how can we factor a monomial out of the polynomial expression 6x to the fourth minus 9x squared plus 15x? First, we want to identify the greatest common factor of the three terms that make up this expression, 6x to the fourth, 9x to the power 2, and 15x. In order to find the greatest common factor of these terms, we're going to look for the largest expression, in a certain sense, which each of these terms is divisible by. We'll do that first by focusing on their coefficients. In this example, the coefficients are 6, 9, and 15. And we'll find the greatest common factor of that triplet of numbers by discovering their prime factorization and noticing that each of their prime factorizations has a 3 in it, and that is the most that these three numbers share in common. So the greatest common factor of 6, 9, and 15 is the number 3. That number will then be the coefficient of the greatest common factor of these three terms. But we're not done yet finding the greatest common factor, because in addition to having a coefficient, each of our original terms also had a variable factor to deal with, which was a power of the variable x. Fortunately, finding the greatest common factor from among those variable factors has a simple shortcut. We need only to choose the lowest exponent that we can find. Since the exponents on our powers of x are 4, 2, and 1 in our three terms, we will choose the factor with the lowest exponent, x to the power 1, to be the variable factor of our greatest common factor. So at the end of this process so far, we've discovered that the greatest common factor of the three terms 6x to the fourth, 9x to the second, and 15x to the first is an expression whose coefficient is 3, which is the GCF of 6, 9, and 15, and whose variable factor is x to the power 1, because that was the lowest exponent on the powers of x in our terms. Great. So I think that was the trickiest part of this problem, but we are also not done just having identified the greatest common factor, because the task in factoring is not just to discover what may be factored out, in this example 3x, but also what that factor must be multiplied by to recover our original expression back again. So what's missing is the quantity in this other set of parentheses that I like to call the leftovers. When 3x is factored out of 6x to the fourth minus 9x squared plus 15x, what remains in that expression? We can find that, most simply I think, by dividing the expressions by one another, dividing them by the GCF. So if I divide 6x to the fourth, 9x to the second, and 15x to the first by 3x to the first, I will discover what belongs in the leftovers. And when we divide a pair of monomials, the coefficients, the numbers, divide. Therefore, the coefficients in my leftovers are going to be the results of dividing 6, 9, and 15 by 3, the coefficient of our greatest common factor. Simplifying those coefficients, we end up with a 2, a 3, and a 5. So those are the coefficients in my leftovers. How about the variable factors? The variable factors we will discover by dividing the powers of x in our terms by the power of x in our greatest common factor. So here, we're dividing two exponential expressions with the same base. And when powers divide, their exponents subtract. So if I were to divide x to the fourth by x to the first, I would get x to the power 4 minus 1, or x to the 3. Likewise, dividing x to the power 2 by x to the power 1 gives me x to the 2 minus 1, or x to the 1. And dividing x to the 1 by x to the 1 gives me x to the 1 minus 1, which is x to the power 0. And because any variable raised to a 0 power is interpreted as the constant 1, in other words, that x to the 0 becomes a factor of 1, which is an invisible factor, making our power of x disappear. So the leftovers, in the factor on the right, have as their terms 2x to the third, 3x to the first, and the constant 5. To finish, we just need to restore the signs that connect those three terms together from our original expression, a minus in front of the first pair and a plus in front of the second pair. We can also clean up our answer by not writing the power of 1 on our exponents of x, giving us the final factored expression, 3x times the quantity 2x to the third minus 3x plus 5. So to factor out a monomial from a polynomial, the first task is to identify the greatest common factor of the terms in that polynomial. We can do that by first finding the greatest common factor of the coefficients, the numbers. That's going to tell us what the coefficient of the GCF is. And then also choosing for each of the variable factors that factor on each variable that has the lowest exponent. So the GCF of the coefficients multiplied by the power with the lowest exponent will give us our GCF that we can write out in the front of a set of parentheses to begin our factoring process. Then we just need to determine what belongs in the leftovers. To do that, we'll divide each of our original terms by the GCF that we found. And when that division happens, the net result is that the coefficients get divided. So in this example, we divided 6, 9, and 15 by 3 to get the coefficients of our leftovers. And then when the powers divide, the exponents subtract. So the exponents that we got on our x's in the leftovers went from 4, 2, and 1 in the original to 3, 1, and 0 in our final answer.